The fourth talk of this session is entitled Composing and Decomposing Op-Based CRDTs with Semi-Direct Products. This paper has been written by Matthew Wiedner, Christopher Meekjohn, Heather Miller, all from Carnegie Mellon University. Matthew will be presenting the talk.
Hello, I'm Matthew, and I'm going to be talking about our paper, Composing and Decomposing Op-Based CRDTs with Semi-Direct Products. And this is work with Heather Miller and Christopher Meekjohn. So to start off, let's say you're building a web app where you have some kind of stored state that can be shared between different users. So this is basically any website nowadays. But some specific examples I have in mind are things like Slack or Facebook groups, or maybe a conference management website. So the usual way you'd build this is you have a server, and when a client wants to change their state, they send a message to the server responds, and then the client updates their own view of the state. Okay, but we know that actually the server is probably not a single machine, but a bunch of machines working together in the cloud using message passing. Now, a lot of work has gone into making these systems efficient and easier to use, but it still can get pretty complicated. It's easy to introduce subtle bugs, and you need a lot of specialized knowledge to write the server-side code. So CRDTs provide an alternative way to build applications that use shared state. The CRDT stands for conflict-free replicated data types. And basically they're like ordinary data types, except that they're shared between a group of users and they intelligently sync up with each other in the background. So as an example of how you might use this, on the client side, you can use this snippet from the Legion CRDT library. So the first two lines here set up the group state basically and connect to each other. And then after that, if you want to have a shared set, like maybe a shopping list, all you do is instead of making an ordinary set, you make a Legion set. And then you can just use this like an ordinary data type. So for instance, you can say shopping.addMilk to add milk to the set. And what this will do under the hood is it updates the local state immediately, and it also lazily broadcasts the operation to other users and replicas, who will then apply the operation to their own copy of the state. And CRDTs are neat because they're a programming language's way of solving a systems problem of how to build these applications with shared state. And in particular, the way you design them is principled and mathematical. So at least in theory, it should be harder to introduce bugs when you use them. So some pros, you have this simple client-side programming model, like I described, where you basically just switch out your ordinary data types with CRDTs, and then they run on top of a generic server. They have minimal latency, they work offline, can support end-to-end encryption. Some cons is that they're targeted at data that's shared in small groups only, basically because everyone has to share the state with each other and sync up, so you don't want the group to be too big. Also, they have automatic conflict resolution, but this algorithm will make some specific choices which won't be appropriate for every app. They're not for data that needs locking, but the biggest thing that I want to talk about is the fact that you have to design the conflict resolution algorithm for each data type, which is a difficult and ad hoc process. So in practice, what this means is that you're restricted to using a few common data types with restricted interfaces, basically whatever CRDT researchers have figured out within the past 10 years. In this work, we present a compositional design technique for op-based CRDTs, which we call the semi-direct product, which is supposed to address the difficulty of designing CRDTs. What it lets you do is you take two input CRDTs, here C1 and C2, you take, and they have to operate on the same state type. You take a bit of extra information in the form of this function that we call the action, and then what you get out is this CRDT that supports the operations of both of their input CRDTs and also resolves conflicts between them in a natural way. You can use this for composition of CRDTs directly, which is where you take two existing CRDTs and combine them to get a CRDT with both of their operations. In practice, usually you can use this to add operations to an existing CRDT. So for instance, we show how to take an integer counter CRDT and add multiplication operations, or take a list CRDT, add a reverse operation, or take a dictionary CRDT that maps keys to values and add a functional mapping operation, which applies some operation to every value in the dictionary. You can also use our semi-direct product for decomposition, by which I mean taking an existing CRDT design and exhibiting it as a semi-direct product of two simpler CRDTs, often commutative data types, which are sort of the simplest type of CRDT. So for instance, if you have a set CRDT, we show how to decompose it into two simpler commutative data types, one that only has add operations and one that only has removes. And likewise, with some generic resettable CRDT designs, we decompose them into the non-resettable and the resettable parts. So to explain our construction, I first want to give a bit more background on how CRDTs work. So recall our system model. When one user updates the state, they update their local state immediately and also broadcast the operation to other users in the background. So the problem can come if you have conflicting operations. For instance, let's say Alice and Bob share an integer, and Alice sets the value to 3, while at the same time Bob sets the value to 5. So then later they'll sync up with each other and they see that they have a conflict. So they have to decide what to do in order to get the same answer. So one main conflict resolution technique that's used in CRDT designs is to make operations commute. So for instance, in the Alice and Bob example, let's say that they're actually counting something, like the number of clicks on an ad. In that case, when Alice sets the value to 3, what she actually wants to do is add 3 to the current value. Likewise, when Bob sets the value to 5, he actually wants to add 5. But these addition operations commute. They'll both get the answer 8 once they exchange operations. So that's fine, we've avoided the conflict. You can also use commutativity to design clever sequence types that don't have conflicts. Another thing you can do is to reason about causality. So I'll go into more detail about what I mean by causality on the next slide. But a simple example is if Alice and Bob share a shopping list. Say Alice adds milk to the shopping list. Later, Bob sees this operation, but he's already bought milk at the store, so he's going to remove milk from the shopping list. Then what a CRDT will do is it'll send out a message to the other users saying, remove milk from the shopping list, but only after applying Alice's operation. So the result is that anyone else will apply add and then milk in that order, so they'll end up in the state where they don't have milk on the shopping list. And thus everyone will end up in the same state. There's no conflict anymore. So in general, when I say reasoning about causality, I mean reasoning about the causal order on operations. This is the partial order defined according to 3 rules, which I'll illustrate using this diagram. So here time goes to the right, and diagonal arrows indicate message sending. Okay, so the first rule is that if some user, like Alice, sends 2 operations in a row, then the first operation is less than the second one under the causal order. For instance, here adding milk is less than adding bread. The second rule is that if, say, Alice sends a message, Bob receives it, indicated by the first diagonal orange arrow, and then Bob sends his own operation, like remove milk here, then the first one is less than the second one. So here add milk is less than remove milk in the causal order. And the third rule is transitivity. So by what I just said, add milk is less than remove milk, and by the first rule again, remove milk is less than add eggs. So then we dictate that also add milk is less than add eggs by transitivity. Okay? So note that this is a partial order. It's possible to have a situation like this, where these 2 add milk operations are neither less than nor greater than each other. In this case, we say that they're concurrent. Then the good thing about causality is that CRDTs can query the causal order. Basically, you can attach metadata to operations when you send them over the network, so everyone agrees on what the causal order is. And then this lets you make definitions, like for a set CRDT, you can say X is in the set if there is an add X operation that is not less than any remove X operation. Okay? Because this rule explicitly reasons about causality, there's no possibility of conflict. Even if people get operations in different orders, they'll come to the same result. And you can see in the example I have here, milk is going to stay on the shopping list according to this rule, because Charlie's add milk operation is not causally less than any remove milk operation. Okay. So again, here are the conflict resolution techniques for building CRDTs, commutativity, and reasoning about causality. What a semi-direct product does is it provides a uniform and reasonable way of reasoning about causality so that CRDT designers don't have to do it from scratch each time. This is good both for coming up with rules, like this rule that I've specified here for a set, and it's also good for implementing them. So if you just look at this definition, it's not entirely clear how you would implement this efficiently without just looping over the full history of operations every time you get a new one. Okay? So what our semi-direct product enables is a new CRDT design workflow. So starting from an ordinary data type that you want to turn into a CRDT, you first design commutative data types for simple subsets of operations, and then you glue together those subsets with semi-direct products, and it'll handle conflicts between the operations that don't commute in a natural way. In our experience, this design workflow works for most existing CRDT types, plus novel ones. Okay, now for the rest of the talk, I want to give an example of how our semi-direct product works. In particular, a simple example, we're going to start with 2 commutative data types, an integer register that has add operations and an integer register that has multiplication operations. And we want to compose them into an integer register that supports both kinds of operations at once. Okay, so an example of something you can do with this data type is you start in state 1, multiply by 3, and add 1. But of course, the tricky part is that multiple users might be making these operations concurrently, and we have to resolve conflict between them. So add operations alone are easy. They already commute, so there's no conflicts. Similarly for multiplication operations, but they conflict with each other. For instance, if Dave and Mary are sharing a counter, and then Dave says to multiply his state by 3, while concurrently, so without coordination, Mary says to add 1 to her state. Then after they exchange these messages, if they just apply them literally, they'll end up in different states. Mary's going to be 6, and Dave's going to get 4. So this is a conflict. Okay? So now to resolve this conflict, you're going to make the choice that in the face of a conflict, adds should go before mults. So basically here, Mary is in the right and Dave is in the wrong. We want to get the answer 6. And our observation is that to make this happen, if you're like Dave here and you get the add and the mult in the wrong order, you can fix it up by acting on the addition with the multiplication. Okay? So here what we say is when Dave receives Mary's add 1 message, instead of applying it literally, he's going to act on it with this multiply by 3 message and add 3 instead. So then he gets in the state 6 as well. We've solved the conflict. And this works by the distributive law of multiplication over addition. Okay? So more generally, if we have a more complicated situation like this one, we make the rule that when you receive an add operation, before applying it, you first act on it by all concurrent multiplication operations that you've already received. Okay? So in this example, Dave has multiplied his state by 2 and then added 1, while concurrently, so without coordination, Mary multiplied by 3 and then added 4. Okay? And now they sync up, so they exchange these operations. So Dave gets the multiply by 3 operation from Mary, he'll just apply that literally. But then when he gets this add 4 operation, he first looks in his history and sees that he's already applied a multiply by 2 operation that is concurrent to the add 4. So he's going to use that as a transformation and add 2 times 4 instead to get 17. Likewise, Mary receives the multiply by 2 operation from Dave. She applies it literally. And then when she receives the add 1 operation, she's going to transform it by her mult 3 operation because that's the concurrent message that she's already applied. So she adds 3 instead of 1. And then they both end up in state 17. So the fact that they both end up in the same state is again just a consequence of distributivity. Another way of stating this rule is that if you receive an add m message from another user, then you turn it into add of n1 times nk, etc. times m, or mult n1 through mult nk, or all the multiply operations that you've previously received that are concurrent to the one you just received. Okay? And this rule is the same general rule that we use in the full semi-direct product construction. Basically, you give some action which says if I receive one operation after a concurrent operation of another one, I'm going to act on it with this action. And this works in general subject to algebraic constraints on the input CRDT and on the action. Okay, so that's all I wanted to say about our construction. Just a quick recap. CRDTs are a nice programming language's way of building systems that act on shared state, like web apps. The way you use them is that programmers just replace ordinary data types with CRDT versions on the client side, and then the server is just a messaging server. If you want more information about these, I encourage you to check out the website crdt.tech, which has a collection of nice resources. So in our work, we present the semi-direct product, which is a compositional design technique for CRDTs. It resolves conflicts between operations by reasoning about causality in a uniform way so that you don't have to. And it enables a new CRDT design workflow where you start with a data type that you want to replicate. You design commutative data types for subsets of operations, and then you glue these together with semi-direct products. Okay, and that's all I have to say. So thanks for watching, and I hope there'll be some questions.
Thank you, Matthew. If you are watching this talk live as an ICFP participant, please remember to join the Q&A session if it is available in your time zone.